Hello and welcome to episode 11 of my video series in which we program an entire video game from scratch, from beginning to end, in the C programming language. So last time we left off in a pretty good place where we have some debug information being drawn to the screen. We drew our little white box here, which is going to end up being, I think is going to end up being our hero, our player. So that's pretty good. I'm just cleaning up a couple things here. I added some comments to my file. Um, Also, I remember last time the compiler was giving us this warning about this function not being inlined, and I tried to disable this warning uh, by adding this pre-compiler directive right here to disable this warning, and it wasn't working. And I was blaming it on Visual Studio, and I think that was probably wrong of me. I probably should not have blamed it on Visual Studio. I think what it's saying is, since it says that the warning originates from this file, standardIO.h, which we didn't write, I think I can probably make it go away if I just put stdio.h underneath this, where this pragma right here, where we turn the warnings down to 3. So let's see what happens. Yeah, and that made it go away. So again, it was wrong of me to call it a Visual Studio bug. It wasn't a Visual Studio bug. It was just being annoying. All right, so next thing I want to do is I want to go down to render frame graphics, where I draw the debug information, and I want to make the text size larger. So let's figure out how to do that. I think I have to create a font. Let's see, yeah, I have to create a font. Do I really want to create a font? You know what, on second thought, that's a little too much work. So I'll just leave it small for now. I do want to turn the debug stuff on by default though, which is perf data. Performance data dot display debug info equals true. So now the debug info will be on from the beginning by default, which is what I want. Okay, so back to this. The next thing I want to achieve is I want to try to get my FPS closer to 60. I really feel like that should be possible to do. But I think in order to do that, I need a better idea of what the current Windows timer resolution is. And I know of one way to do that. Well, actually, my first thought is to use this function called time get device capabilities. And as you can see, it takes in a time caps data structure. And if we look at the time caps data structure, if I look at it, let me run to cursor right here. Time. Okay, it has two members in this data structure called period min and period max. So the reason why that is useless to me is that it doesn't tell me what the current timer resolution is. I have the minimum and the maximum, but not the current. So the only way I know of to get the current timer resolution is with an undocumented Windows API function, and I believe it's called ntquery something or other. Let me look it up. ntquery, yeah, ntquery timer resolution. ntquery timer resolution. And as you can see, nothing is coming up in IntelliSense, and that's because this function is not defined anywhere in Windows.h or any other Windows header file. But I know it exists, and in fact, I know that this tool that I've been using, the sysinternals tool, ClockRes, I know that that is the function that it uses, and I can prove it by using, let's see, where is program files? I don't remember. Dump bin.exe. Not there. Let's try program files x86. There it is. If I go to this directory and I type in dump bin, and then I dump tools / clockres.exe, and then I think it's imports. So this should dump out the functions that are imported by this executable, and it did that. And if I look through all of these, I should find an ntquery timer resolution function somewhere in here. Query performance counter. I don't see it. Huh. No. That did not go how I expected it to. Anyway, so I think I'm almost positive that this ClockRes executable uses that function ntquery timer resolution, and it comes from, I believe, kernel32.dll, I think. If we run the same tool on Windows System32 kernel32.dll exports, and then try NTDLL. Okay, that's more like it. NT query timer. There it is. Okay, so all of that was to show you that if I run the dump bin tool and I run it against the ntdll.dll module and I list the exports of ntdll, you will see that that ntdll does indeed export a function called ntQuery timer resolution. And like I said, it's not defined in the Windows API, so it is undocumented, and you're technically not supposed to use undocumented functions because undocumented functions are subject to change. Microsoft reserves the right to change them at any time, so you shouldn't, as a general rule, build your applications to rely on undocumented behavior. But NT-Query Timer Resolution has been around for, since, the beginning of Windows NT, so over 20 years now, and it's never changed. So I think it's probably pretty safe to use it. That being said, we're going to have to do something funny since it's not defined or not declared in any of our header files. We're going to have to go and load this directly out of the NTDLL module that resides on the user's machine. So let's go ahead and do that. Let's go ahead and do that. Let's see, handle to a module. NTDLL module handle. Oh wait, I don't want that to be a global. There's no reason for that to be a global. My apologies. Module, NTDLL module. NTDLL module handle equals get module handle a NTDLL.dll, and it's going to search, the system path, and it's going to find this module in the c:/windows/system32 directory on every Windows machine that this ever runs on. Every user mode process loads this DLL. I think that's an accurate statement. I wouldn't bet my life on it though. I could be wrong. Okay. Message box A. Couldn't load NT or NTDLL. Exclamation message box OK, and go to exit. Okay, now that we have a handle to the NTDLL module, I'm going to export the NTQuery timer resolution function from that module. But first, before we do that, we need to define a new type, and I'm going to put it right here. Def long NTAPI star NTQuery timer resolution. NTQuery timer resolution. Out. Long. Minimum resolution. Maximum resolution, and actual, or should I say current resolution. Let me read that, make sure everything looks correctly. Everything looks correct. Long. It does. Okay. So now I can define a new global variable of that type, essentially. So int query timer resolution, int query timer resolution. There. Now I simply need to make this variable point to the beginning of that actual function, int query timer resolution. So I'm going to do if int query timer resolution equals int query timer resolution get proc address, which is a get procedure address of, and then we're going to pass it in get, oh, there's no A on it because it doesn't take any strings as input, so, oh wait, yes it does. int DLL module handle, so it's going to take in the handle to int DLL, and then I'm going to ask for the address of this function, int query timer resolution. Get proc address, long pointer to a constant string. That's interesting that there's no ASCII or wide version of this. I don't know why there wouldn't be. That's interesting. Anyway, so if it fails, it's going to return null. And basically, couldn't find the int query timer resolution function in ntdll. All right. Now all that's left is to call it, but we need, let's see, int query timer resolution, and it takes in unsigned long variables. So let's go define these. And I'm going to put them inside of our gameperf data structure, because that seems like a good place to put them. Long minimum timer resolution, maximum timer resolution, and current timer resolution. Now back over to main.c. gPerformanceData.minimum, address of gPerformanceData.maximum, and gPerformanceData.actual or current. Let's go back down here and display these things. 1, 2, 3. Min timer resolution. Max timer resolution. And current timer resolution. And these are, even though these are long variables, these are probably in microseconds, right? But I want to turn them into floats. Because obviously yeah, it probably returns them in microseconds. I'm just kind of assuming that it does. All right, let's just go back here. Dot min divided by $10,000. Let's try that. 10,000.OF. And then max timer resolution 10,000.0F divided by okay. Oh yeah, we need to change. This moves by 13 pixels every time, so this will be 26, 39, and 50 watt. Alright, let's see what happens. Build errors. Syntax error. Oh. Yep. Okay, so that looks like it was probably correct. Minimum timer resolution is 15.6 milliseconds. The max timer resolution is 0.5 milliseconds. And the current timer resolution is 1.0 milliseconds. Let's get a little bit more precision on that, shall we? Two, and line it up a little bit. Oh, here we go. And timer. There we go. Let's see what it looks like now. There we go. 15.63. Okay. Okay, that worked out well. So now that we know the current timer resolution of the machine that we're running on, let's go back down to our main game loop, where we start our timer, we dispatch our window messages, we process player input, we render frame graphics, and then we stop the clock, we calculate our elapsed microseconds, and then we enter this loop, where what I want to do is I want to sleep in the smallest increment possible unless the sleep would push us beyond our target microseconds per frame. So I feel like I should do something like if elapsed microseconds per frame plus, no, if elapsed microseconds per frame is less than target microseconds per frame. No, it's not right. Hold on. Target microseconds minus gperf data dot no thanks no IntelliSense, I don't need your help. Don't need your help at all. There. And I'm going to put it at the end instead of the beginning of the loop, and I'm essentially saying if the elapsed microseconds per frame is less than our target minus the timer resolution, then go ahead and sleep. So that way, for example, if my timer resolution was 15,000 milliseconds, then I couldn't afford to sleep for 15,000 milliseconds if I had already spent 8,000 milliseconds completing the frame. I couldn't afford it because then when my thread finally wakes up, I will have completely gone past my 16,667 millisecond target. So essentially what I'm trying to accomplish here is I'm trying to be precise, and I'm trying to get the best of both worlds by I'm sleeping, so I'm not burning up the CPU, but I'm also getting a precise target FPS. So let's see if that gets us any closer to 60. It does. Oh my god, it works perfectly. That's amazing. So yeah, that actually worked perfectly. I get a consistent, exact 60 FPS, which is awesome. I'm really happy about that. So pretty soon you will finally not have to hear me talking about this timer resolution thing ever again. All right, arithmetic overflow, casting to an 8-byte value. Okay. Let's make sure everything is okay. That is working perfectly. So my only question, I'm still sort of concerned about what might happen on a computer where the timer resolution is 15 milliseconds. I'd be really surprised if it still works perfectly. But if it did, that means that we will have accomplished our goal of getting a perfect 60 FPS without modifying the global system timer resolution, which is something to be proud of because that's something that everyone else does, and Microsoft says don't do it. So I'm being a good citizen and not doing it. I'm not modifying the global system timer. So let me just look at that again. That's that FPS of 60.0, and it's steady and unwavering. It's beautiful. That's awesome. Okay, what else? What else? There is something else that I wanted to look at, and it's going to become another big topic. Uh, it's another performance topic. So if I run my program right now, you can see in the top left-hand corner of your screen, if you squint, I'll have to put in a bigger font for you because that one's pretty small. But anyway, if you look up there, you'll see I'm getting a raw FPS of about 480. Sometimes it gets up to almost 500. Sometimes it's around 475, something like this. Now that seems pretty fast, but we're not doing anything right now. I mean, really, all we're doing is painting the screen blue, and we are drawing a little white square. Those are the only two things that we're doing. And I feel like with doing that little amount of work, we should be getting even more frames per second than what we're getting right now. I mean, my processor is something like 3 gigahertz, so I have an extremely fast processor for, you know, such a small amount of work. I don't know, I feel like this should be running faster. So what I'm going to introduce at this time is a concept called SIMD, which stands for single instruction, multiple data. So I remember when I was pretty young, kind of a young teenager, toward mid 90s, like 95, 96, 97, I started seeing these commercials on TV by Intel and later even AMD. AMD had one also. They actually had commercials back then. You know, when they would do like the Intel Inside or Pentium Inside, I can't remember what it was, where they would like have this computer graphics of like going through a computer, and it was to advertise the capabilities of their new CPUs and how fast their CPUs were. And this was very exciting to me when I was like 14 years old. But anyway, part of the technology that they were developing back in those days, back in the mid to late 90s, was this right here, SIMD. And what it is in essence is it's a set of registers on the CPU. And I think, you know, we've done a little bit of assembly on this channel so far. You may have seen register names like EAX or RAX. Let me go ahead and run to cursor here. Yeah, see, we're like here, you're loading 30 hex into this register R9. I'm loading a pointer to this string into the register R8, and I'm loading the pointer to that string into the register RDX. And then this is how you basically zero out a register. I'm calling XOR, which is exclusive OR, on ECX against itself. So like no matter what ECX is, no matter what the contents of the register is, if I XOR it with itself, the result will always be 0, because remember, exclusive OR means that it can either be one or the other, but it can't be both. So if I XOR something with itself, it's always going to equal itself, therefore the result will be false. Anyway, that's the easy way to zero out a register. But anyway, I digress. These are just some of the registers on our CPU, but the CPU actually has other registers too, and I think I can view them. I think I can view them in one of these Windows registers right here. Here we go. These are actually almost all of the registers on my CPU. Nope. Here we go. If I right click, notice I have only the regular CPU registers selected, and I have, you know, AX, BX, CX, DX. But if I right click, I can actually select more of them: MMX, 3D Now, SSE, AVX, AVX 512, so on and so forth. These are the SIMD registers, the newer type of registers. So the first version that Intel came out with was called MMX, and it's these additional registers that, you know, back in these days, CPUs were, you know, they were only 32-bit, so 64-bit registers didn't exist yet. However, the MMX registers, they introduced 64-bit registers on a 32-bit CPU, so you could actually jam an entire 64-bit thing inside this register and then operate on it in such a way that you were essentially operating on two 32-bit things at once. So, for example, if I wanted, I could just do one instruction and say, I want to add 8 to both sides of this 64-bit register, and then I can go and retrieve it, and I would have 2 copies of these 32-bit numbers, but I only had to execute one instruction in order to perform an operation on both of them at the same time. Okay, so essentially I could do work twice as fast. Okay, so if I had a whole bunch of data, like for example, a video game or even just a photo or rendering video, these are the sorts of things that computers do where you need to process, you know, thousands and thousands of pixels in as quick as possible. And say I wanted to perform an operation on all, if I wanted to perform an identical operation on all these pixels all at one time, like for example, let's say, you know, alpha blending, for example, or if I wanted to fade them all at the same time, then I could load them up into these registers that were extra wide, even wider than the general purpose registers, and basically do it twice as fast. So that was the first iteration of Intel's technology. Notice that 3D Now is grayed out, and I imagine that's probably because I don't have an AMD processor, but it's essentially the same thing as MMX. The next one that came out, though, was SSE. Now, SSE introduced these registers, the XMM0 through XMM16 or 15. Now, notice these are 128 bits wide. So now XMM, these XMM registers, these 128-bit wide registers, are essentially to 64-bit registers, or 64-bit CPUs, what these 64-bit registers were to 32-bit CPUs. I can jam 128 bits worth of data into each one of these registers, and then I can perform one operation on I can perform one instruction on this 128 bits worth of data, and then I can fetch and split that up into 4 pieces and have essentially 4 32-bit pieces of data that have all gone through the same CPU instructions, or that same operations. Essentially, you know, I'm like practically quadrupling my throughput at that point. So hopefully that was clear. Let's see, where's my, yeah, let's look it up. when did you come out? Okay, the first use of SIMD instructions was way back in 1966. Let's look for... Yeah, see, small scale 64 or 128-bit SIMD became popular on general purpose CPUs in the early 90s and continued through 97. And then you will go on to see the history of like MMX and SSE and SSE2, etc. So essentially, if I want to use this technology, I'm basically bounding myself to newer processors. Okay, if I want to say if I wanted to use say AVX 512, and yeah, those are 512-bit registers. I can't. It means that my program would only run on hardware that actually physically has those registers present. And I don't think I even have them on my processor, which is only a few years old. Meanwhile, on the other hand, if I go back to SSE, I think that basically every processor made since probably like 2002 or 2003 can handle SSE instructions. So, pretty much any processor made in the last 20 years should be able to handle SSE and SSE2 instructions. So I think that's probably the medium that I'm going to go with. I can't use technology that's too new because then I wouldn't be able to run on any of the older processors. And I don't want to use technology that's too old like MMX because MMX is not as powerful. So I kind of have to choose something in the middle here. Alright, so I would definitely go and read that when you have some free time. There's another website that you need to see. Intel Intrinsics Guide. Intel Intrinsics Guide. This is a very cool website that essentially you select what technology you want to use, and it will give you a list of Intel or CPU intrinsics that you are allowed to use that are supported with this family of CPU technologies. So, for example, if I click SSE2, it will only show me SSE2 instructions. And essentially, what you have here, you have 128-bit data types, and then you have functions that operate on 128-bit data types. And you can add and subtract and compare and bitwise and bitwise not, and do all these things. And they have probably a 3,000 page manual that probably describes all these things. If you click on something, it will give you a description of what they all do. Okay, so that's kind of a general introduction to SIMD. Now, how do we use it in our game? First thing we need to do is we need to include something. And I think it's called EMMIntren.h. And I think let's look that up too, because there's several different header files that EMMIntren.h. Yeah, see, there's different header files. Or wait, did this tell me? No, this didn't tell me. There's different header files for different technologies, like XMM Intren. Yeah, see, there's an XMM Intren too, and the way these header files is essentially like, there's one for SSE, there's one for SSE2, there's one for AVX, and then there's another header file that like includes all of them together, all this kind of stuff. And I don't remember exactly how they go, but I do remember that I think that's the one that I want, is EMMIntrinsics.h. that will allow me to use things like that is a 128-bit data type right there. So that header file gives us a whole bunch of new data types that we can use, including 128-bit data types. So what we can do with those, and we're going to use these 128-bit data types to put them into these XMM registers, 128 bits at a time. So now we can essentially work twice as fast or thereabouts, because we no longer have to work 64 bits at a time. We can work 128 bits at a time, right? Okay, so now what kinds of functions would benefit from this behavior? Well, I'll show you. If I go down to render frame graphics, and this right here is the exact sort of thing that would benefit from this kind of behavior. What if, instead of laying down 1 pixel at a time, like I'm doing now, what if I could lay down 4 pixels at a time? So let's see, this is blue. So what if I changed pixel to quad pixel? And I'll just initialize it like so. B G R A, and then BGRA, BGRA, blue, green, red, alpha. And I don't need that anymore. Oh, and since this is no longer, this is actually a pointer, we're making it a pointer to a pixel 32, because, all right, let's, hold on. Pixel 32. There we go. So instead of just 1 pixel now it's a new thing called a quad pixel. It's an array of pixels. It's 4 pixels, all smashed together. So now in our for loop, oh, and I should mention that this is going to work smoothly. This is going to work smoothly because our screen resolution is a nice and tidy multiple of 4, right? So what is it? 384 times 240. Is that our size? I still can't keep it straight in my head. 384 by 240 equals that much, divided by 4 is, okay, so now instead of doing 92,160 mem copies, we're going to reduce that to 23,000 mem copies. So we're going to be speeding this operation up by quite a bit. We're not going to need that anymore. We're going to be using, all right, let's use mmstore SI128. Surfit G render surf G render surface. Oh, G back buffer dot memory, and then our offset, which is going to be X. And then put our quad pixel right there. Okay, what is the... Oh, suppose I should stop right there. Okay, so our quad pixel is 128 bits because it's 4 32-bit pixels. Saying incompatible. Well, what if I just cast it? So let's make this okay. Now let's see what happens. So I think when I run this now, what should happen is I've got this 128-bit data structure. This is going to store it all in one instruction. So I should pretty much quadruple my throughput on this operation right here. Let's see what happens. Okay, perfect. Now, if you look at the upper left-hand side of the screen, you'll see that our frames per second has gone from, how much was it before? Maybe 400, maybe 450 to 500. Has now gone up substantially, like multiple times, to now we're looking at over 2,000 frames per second, 2,500 frames per second. And it's all from using the MMX or SIMD registers and intrinsics. So yeah, awesome. See what the time is looking like. About 56 minutes. Okay. That is awesome. I think we will probably use this more in more interesting ways in the future. But just this right here has gotten us a huge performance gain. I think in the future we may use it. We might use it to do alpha blending, but then again, we might not do any alpha blending at all. The original NES, for example, was not capable of alpha blending. So we may actually, instead of doing alpha blending, we may just do transparency using a particular color. For example, when we first created our window, remember that I made the background of that window a quote-unquote hideous purple color, which was essentially full red, full blue, and zero green. And it makes this nasty like pink purple color. That color is it's so terrible that it is unlikely for that color to show up anywhere in our game naturally. So anytime we see that nasty purple color, we'll be able to immediately spot it as we probably are doing something wrong, right? So that color is also used as a color to show transparency in our sprites. For example, if I were to draw something, like let's edit and install when I exit, canvas size 16 by 16 pixels. And by the way, this is something you're probably going to end up watching me do a lot on this channel as well, is art, because Right now we've been doing only programming, but we're going to make a video game, so at some point there will come a time when we're going to need some artwork too. So um, you're probably going to end up watching me do a lot of art as well. But anyway, so let's say going to do that. Going to make this pixelated. There we go. Our perfect 16 by 16 circle. Oh, that's not perfect though, is it? It doesn't matter. Just for demonstration purposes. And let's paint the inside of it red. So we got a red circle. Now, if I draw this, if I make this one of our sprites, for example, this red circle, and I say, I would like for this to be transparent so that whatever this red circle is sitting on top of, I want to be able to see the floor underneath it, right? I don't want this white, I don't want these white corners. So what I will probably do is I will get the same color, which is our hideous purple color, or sorry, no green, full red and full blue. I will get this same hideous purple color and I'll paint the edges like this. And so when I load this image into our program and I go to draw it onto the screen, I will say, anytime you encounter this color, just don't draw this pixel, and it will achieve the effect of transparency for us. So that's probably what I'll do. I doubt I will do any alpha blending, although I might. Haven't decided yet. Anyway, if I do alpha blending, then that's another operation that is greatly sped up by using SIMD as well. So, all right, so let's see. Let's go ahead and make that into its own function. We'll call it clear screen, and we can clear it to any color we want. Just 2 underscores here. Do I want this to be passed by reference or passed by value? I think it's always, that's a topic that we'll talk about next time, is passed by reference versus passed by value. Because that's another thing that makes a big difference in terms of performance. But I'll just leave that as it is for now. So copy that, declaration, and then we'll go down here and make a definition for it. And then render frame graphics. Clear screen, render frame graphics. Okay, and of course, we can make this any color you want. That would be like a gray, wouldn't it? Let's just stick with blue for right now. There we go. So we're getting 2300, 2400, 2200. Interesting. Oh, and then I can change this cast. Actually, no, I can't change this cast. If I do this, I think the game will crash because this is going to put the arithmetic off big time. So I'm not going to do that. And then what is always in line? Force in line. It's force in line. Now, I think I didn't really need to do that because I think there's like a 99.9% chance that the compiler was already going to inline this function on account of how small it is. But, you know, it's not like it's not like forced inline is going to hurt. So, okay. So, I think that's about it for today. And as always, thank you for watching. And if you have any questions or comments on the video or any of the videos up to this point, please just go ahead and comment on YouTube on the videos. You can also find me on Twitter at Joseph Ryan Reese. Don't forget that there's a GitHub repository for you to follow along. And I guess that is it. So I will see you next time. Enjoy the rest of your weekend. Bye.